last time we left, I was like interrupted by somebody. Yeah, the hostel isn't really a good place to be filming these videos. But anyway, let's just get started once again. So question number 7. Also, like I actually searched this up. So the value of g is something like 32 feet per second square, which is, I don't know, it could have been really useful for me. But anyway, let's just get it started. Uh, so so approximately 32. But yeah, a baseball is hit when 3 feet above the ground. It leaves the bat with some initial speed, making an angle of something with the horizontal. Assume there is a linear drag. So just like the last question, uh, drag coefficient is this k was given to us. Well, that would be our drag coefficient. From exercise 6, find a vector form for the path of the baseball. Cool. So you got x y is equal to this stuff, right? Cool. Uh, so the initial speed was 152, and that upon k is 0.12, isn't it? So just divide by that. Sure. So that's 150 is 12 and you're 32. That's not a good idea. Yeah, whatever. So it's just 15200 upon 12, whatever that number turns out to be. That. So I'm just gonna find what vx, vy are first. Yeah, well, okay, this time so at angle of 20 degree. So once again, it's not like I'm going to be able to solve this because I don't know what cosine 20 degree is. But yeah, so just you got 15200 upon 12 sine 20 degree, and all of this is in like feet per second. Right, now what you want is, I mean, okay, that's kind of all that we were given. Sure, so find a vector form of the path. So our x thing will just be like vx, which is this, times 1 minus e power all that stuff. So just 1 minus e power negative k is just this thing, 0.12, right? Right, a drag coefficient of this, but you don't, so don't you like mean units for this? So it's something like acceleration is just minus k times of v, so you already got like dr upon dt, so it's upon second or something like that. 0.12 what? I think it's 0.12 per second. It's probably the only sane explanation. Yeah, this as well, it should be like per second. Oh, this 12 should not be there actually. Neither should this one be there. Okay. So that what is this wire? Okay, so x will just be like vx upon k, which is I'm assuming it's like 0.12 per second. Yeah, that's the best we can do. So upon k, and then 1 minus e power negative kt, and then y would just be something like vy upon k, and other stuff. So yeah, just 1 minus e power negative kt, but then that plus this, so g by k square, right? And this thing, so 1 minus kt, and then minus e power negative kt. Cool. These are your equations. Obviously, so since you don't know like what cosine 20 degree is, sine 20 degree is, you will just have to calculate this like on a computer. I guess finding cosine 20 degree wouldn't be that hard. I mean, some basic algebra, but whatever, I won't do that. Okay. Yeah, you will have to solve 5-degree equation. Not a good idea. Sure. So okay, A is done. Then we have how high does the baseball go and when does it reach the maximum height? Yeah, sure. So just it will be something like u upon, so uy upon sine theta, uy upon g, well that times of, yeah, I mean that is kind of it, right? So just mgh equal to sure, that gonna work. Something like gh equal to half uy squared. So your h will just be something like uy squared upon 2g, right? So what is uy squared? It's just this quantity. So it's just like Vy square upon 2g. That's how high it will go. That's it. Sure. Okay, next. I won't be calculating any of this really. I could put g equal to 32 and all that, but let's just let it be. We can do it on a computer. Okay, and when does it reach the maximum height? So it reaches maximum height at Vy upon g. Right. C is find the range and flight time of the baseball. So the flight time is pretty easy, just 2 Vy upon g, and the range would just be the usual thing. So just 2 Vy Vx upon g. Yeah. Okay. When is the baseball 30 feet high? Or you could just be doing it slightly differently. You could be doing like 152 sine of 40 degree, all that stuff. 152 square. Sure. I'm not gonna do that. Just put it in the computer. That's the best way. You might think I'm just being lazy and like really just avoiding stuff, but really, I don't want to be taking cosine 20 degree and all that. So when is the baseball 30 feet high? How far is the baseball from the home plate at that height? When is the baseball some certain distance high? Sure. So I think the first time that it really happens, right? Yeah. When does that happen? That's the question. So you already got your y coordinate like this, right? Oh, okay. So this is a problem. In my last two, I can't do this, right? No, there's a drag force. I can't just be doing that. So to reach the maximum height, what will happen is that, right? Ah, that's a problem. Right. So you'll just have to see when is this y dash equal to 0, or when is Vy, not Vy. What should I say? Vy compared to the velocity, when is it 0? So I'm just gonna see when that happens. So it's something like Vy upon k times k power negative kt plus g upon k square, just a bunch of constants. It's got minus k, k plus kt. Sure, we want this to be 0. This is also just kt over there. Yeah. Oh, it's not plus kt, it's supposed to be e power, right? So just plus k e power k negative kt, right? What does this give us? So it's something like Vy e power negative kt plus, or actually it's a minus, it's just minus g upon k. Yeah, I guess that's okay. Plus g upon k e power negative kt, that this thing is has to be equal to 0. Sure. So that just means g upon k equal to Vy plus g upon k. Right, you get the thing. So just e power negative kt, that's equal to g upon Vy k plus g, or you could say that k equal to natural log of that, the inverse. Not yeah, right. So e power kt, that would just be that. So it's something like t equal to 1 upon k natural log of g plus, what was this again? Vy. So k Vy upon g. Yeah. So that's when this will happen. This will be my answer. So whatever is the y value at that point. Yeah. I mean, I can just plug that in and see what's gonna be the value. So plugging that in, what you get is, just get Vy upon k, and then also it's 1 upon k and all that stuff, huh? So 1 minus e power, so negative natural log of all of that, right? So just natural log of g upon all that, sure, and e power that, so just g upon all that. So this quantity just happens to be like g upon g plus k Vy plus g upon k square minus k times of this. So that I'll just, that will be like 1 minus this stuff, and then minus kt, so minus k times of this quantity. So this just happens to be like k Vy upon g plus k Vy. Similarly over here, just k Vy, all that. Now this k cancels with that, this k cancels with this, and you have 1 upon k over there. That's okay, right? So what do you just have? Just have Vy plus g by k, right? Combined. Yeah, for this stuff, so it's just Vy upon g plus k Vy. Oh, that's pretty nice because this cancels. You just got Vy upon k, right? So Vy upon k, and then you just got minus. I hope that was correct. Wait, it wasn't. It wasn't. It's not a plus, it's a minus. Okay, cool. So what do you, so this is supposed to be Vy, sorry, I don't know what I wrote. Right, now what? That's a good question. Now what? Something like 1 upon k, or I should say Vy upon k, that times of k Vy minus g upon k Vy plus g. This is quantity, right? And minus all that stuff. So just minus g upon k square natural log of 1 plus k Vy upon g. Yeah, that's the quantity. Yep. Okay, cool. That's fine. Let's go to the next thing. So that was just B, right? What about C? C is find the range in flight. So you would want when is y equal to 0. Why is it getting so much weirder suddenly? Okay, fine. These are our fundamental values to calculate everything with. These are our equations. Right, but B, then C thing is, C is when is the baseball 30 feet high? Oh no, so we have to find the range in flight first. Sure, so when is this going to be 0? That's the question. So we will just have Vy upon k. I'm just gonna call this V for now, because that Y thing is hard to write. So V plus V upon k plus g upon k squared, that times of 1 minus e power negative kt, right? And then that's equal to this thing, so it's just equal to g by k times of t. So what does that mean? That just means that t upon 1 minus e power negative kt, that is equal to, so if we just divide by g by k, so just, you know, v by g plus, is that g by k or k squared? No, it's g by k, sure. So just 1 upon k, huh? Yeah, right. So now whenever this condition is going to happen, how do we solve that? Right, when would y be equal to 0? That's not something we can solve directly, unfortunately. You'll need a computer to do this thing. Okay, any idea on how would I be able to solve this? I mean, this whole thing is just some sort of a constant, so let's just call this whole thing as some constant a, so this just, or let's call it 1 upon a. So essentially all you're getting is that at equal to 1 minus e power negative kt, right? Or at plus e power negative kt minus 1 equal to 0. So that's a function of this thing. Now we want to figure out when this is going to be happening, right? This is going to be 0. Yeah, T Newton-Raphson method, that's probably the way to do it. You can certainly deal with a bunch of approximations and just like numerically figure out stuff. So let's call this thing as f. What's f dash? That will just be equal to a plus a minus k power negative kt, right? Right, cool. Now what do we do in the Newton-Raphson method? Just have this curve or whatever. This is your xy coordinate. So just find the tangent, right? And figure out what this thing is. So the slope of this will just be f dash. Let's call this x dash comma 0. So what we just have is y upon x minus x dash. That should just be the slope, which is f of x. So f dash of x, sorry. And y will just be f of x, obviously. So that just means like x minus x dash is equal to f of x upon f dash of x. So then x dash is just equal to x minus of this. Right, that seems like it. Yeah, I mean that's kind of a thing. So we just, in this scenario, what would happen is this will be like t sub n plus 1, that's equal to t sub n minus whenever this happens. So just, yeah, right, whatever f is, which happens to be this stuff, oof, oh, it's gonna be a long day. But yeah, so it's got 80 plus e power negative kt minus 1 upon the derivative, which is a minus e power minus k e power negative kt. Yeah, wow, now this is just really bad, isn't it? But sure, so that's the thing, it's tn over there, right? That's a recursion formula. Where do you start particularly? I guess a good starting point would be when you just set this to 0. So it will just be 1 upon a. So you can just set t0 equal to 1 upon a and just do this thing. And there you go. See, I think this is why, like, yeah, you just have to feed all of this in a computer. And I'll do that once I'm done with, like, writing the formula for it. Because I don't see another way. Yep, that looks okay. Okay, cool. So that is C. What about D? When is the baseball 30 feet high? Once again, the same problem. So you will, rather than solving for this, now you'll just have y is equal to all of this minus 30 feet, right? It doesn't really solve anything, unfortunately. Sure. So just say it's some h feet high, right? So you just have like, when is this thing going to be equal to 0? Let's see, what can we do? So you would just be having this cheap idea. Yeah, I mean, you will just have to do it at any point. So let's just try to solve that. So So once again, what we want to figure out is n is y equal to h, right? Does that happen? Which is to say, just have vy upon k plus g upon k squared. Wait, this is in fact plus, isn't it? Right, so why was that being negative or something? I don't remember that. Oh, because it was a derivative of it. Sure. That makes sense. This thing is not a derivative, it's just... Okay, so g upon k squared, all of that, and that times 1 minus e power negative kt, and then we'll just got this stuff, so it's just minus g by k times of t, and then that should be equal to h. So just multiply this whole thing by k. So yeah, just have vy plus g by k times t over there, 1 minus e power negative kt, that's equal to hk plus gt, right? So that just means hk plus gt upon 1 minus e power negative kt, that's equal to this stuff. So yeah, we need a better thing than this, don't we? Vy plus g upon k, let's call this thing as 1 upon a, right? I guess so. Oh, there we divided by g, right? We can do the same thing over here as well, just divide by g, right? So over here it just becomes like t plus something. Just for convenience. Right, because it's like gonna match with the last time in that case. Okay, cool. And then what? So this just becomes at plus ahk upon g is equal to 1 minus e power negative kt whenever this happens, right? Which is the same thing as saying at plus e power negative kt plus ahk upon g minus 1 equal to 0. Once again, call this an f of t function. Then f dash of t, that will just become the same thing as before. All of this is just some sort of constant, so none of that matters, right? So what does this mean? So once again, just set t0 to be, for t0 just set this thing to be 0 or something like that. So then this just becomes something like yeah, just 1 upon a minus hk upon g, right? But then so tn plus 1 will just be tn minus, so what is your f of t, which is just this quantity. And by the way, I'll actually have to code all of this eventually, so yeah, wish me luck. Atn plus e power negative ktn plus all of this funny constants. Right, and that's gonna give me a good approximation of the solution. Problem is I can't really just find an analytical solution to this because you got these weird exponentials and all that, so this is the best I can do. Yeah, okay, let's go to E. So E is a 10 feet high outfield fence is something from the home plate in the direction of flight of the baseball. Sure. From the home plate. What's a plate? Direction of the flight of the baseball. Okay, let's try to do it. So this is where the baseball was hit. Okay, at 10 feet high. So this guy, not guy, but this is a fence which is 10 feet high. It's how 340 feet away, right, in the direction of the baseball. What are you seeing? The direction direction of the flight. Okay, fine. Just on the plane, right? The vertical plane. The outfielder can jump and catch any ball up to 11 feet off the ground to stop it. As the batter hit a home run. Oh, so we are saying he can jump to 11 feet from the ground to stop it from going off the fence. Catch any ball up to 11 feet. So it's an outfielder, right? So I'm assuming he's at the fence. So it will just be like, yeah, sure. So it will just like be one more feet that the ball has to pass. So if the ball passes something like this, then you're done, pretty much. Yeah. So the only the only thing that we really have to look for is like whenever x is equal to 340, what should happen is your y should be bigger than 11, right? Let's call this thing as r, or I don't know, capital X. Let's just call this actually as x. And so y must be bigger than 11. Let's call this thing as h, right? H is 11, x is 340, y is what? That's the question. Alright, cool. So once again, our equations for motion, those are these. So you're saying that x, which is this quantity, is equal to 340. I mean, it could be any value really. So just got kx upon vx. That's equal to 1 minus e power negative kt. So just got e power negative kt, that's equal to 1 minus kx upon vx. Right. So just t is equal to negative 1 upon k, natural log of all of this. What's this going to lead to? Sure, so just t equal to 1 upon k, natural log of vx upon vx minus kx. So you got the value of time. From that you can figure out some stuff. So what you want to figure out is the value of y. So y will just be this thing. So y will basically be like vy upon vx times, well, yeah, x basically, right? Plus so just got g by k squared. So g by square upon this constant, so vx upon k is just g by k vx, and then you got the same thing, just x over there, sure, and then you got finally minus g by kt, right? And you know what t is, so all of this is going to be a piece of cake now. So just have y is equal to vy upon vx plus g upon k vx, or you could just put the vx outside. So yeah, sure, just like vy plus g by k, and you got x upon vx, right? And then minus gt. So t is just this quantity, so it's minus g upon k natural log of and that pretty much like dictates the value of y. So what should happen is that this should be bigger than h. I mean, we have to figure out what this value is. Once we do that, we figure out everything essentially. This should be just some calculation, so you can just start putting in values at this point. Right. This is, I think, something we can actually just do directly. So what's viva? Oh, right. Sine 20 degrees. I don't know that. Oof. Yep, it had to be that way. So I'm just gonna feed this into a computer at some point. So y is something like has hit so it's like what is it called? What is it called again? A home run, right? So home run is equal to, so if I just put an indicator function, so it's just basically like if y is bigger than h, you are done, you have a home run, otherwise no. Right. Okay, next. F, it's not, so just question number 8. 8 is considered again the baseball problem. Really, this time assume that the drag coefficient is used. Once again, it doesn't matter. I've just solved it generally. Setting is gust of wind that adds a component of something with the initial velocity of at the instant the baseball is hit. So the only so it's basically all of the same stuff as before, right? Find the vector equation. We found how high does the baseball go and when does it reach the maximum height. We did that. Find the range and flight. Yes. So when is the baseball some feet high? So at some h value, we already found something like that, right? At 20 feet high, outfield fence is 30. Sure, the same thing as before, just changing numbers. As the yeah, right. So okay, now it's an extra question. If yes, what change in the horizontal component of the ball's initial velocity would have kept the ball in the park? If no, right, okay. So wait, what? In the ball's initial velocity. So it's okay. So you're saying like, how should I change Vx so that this whole thing changes, right? Okay, cool. So basically, like whenever y is equal to h, you would want that particular Vx value, right? So for e, it would be something like, okay, cool. So you got your y. So you want the y to be equal to h. So it's something like h is equal to. So you want to solve for Vx particularly, right? That's a messed up scenario. You already know all of these other things, this x and all. So it's just something like, let's see what's gonna happen. Yep, so you can just use the positive word there, right? It's positive natural log of that looks okay, fine. So our h thing will just be so you got all of this constants, so just vy plus g upon k, that times of x, and this times of 1 upon vx. So 1 upon vx is what will our variable be, so just this plus, or you could just say natural log of 1 upon vx is a better variable to use. Sure. So it was something like, if we just set like let's call this thing as q. Q is 1 upon bx, so this thing just becomes e power q, right? And plus g upon k, then you just got like natural log of 1 minus kxq, right? Wait, that's an e power. So okay, now let's, yeah, I mean that's okay, that's fine. It's not e power q, it's just q itself, right? Sure. Sorry. Fine, I mean that's kind of okay. So now the point is, you have to figure out, once again, this is also doable by, or what is it called, the Newton-Raphson method, because you got these functions which are incompatible, like they can't be solved, right? Whereas one of them is an increasing function, this is a decreasing function, so it's not like you just have to figure out like when is this going to be 0 or something like that. Might not have a point like that. But yeah, so the point is to figure out this thing's solution in q, and then inverting that to get Vx. How would I do that? I just gotta take the derivative or something. So let's call this thing as f of q. So let's just first name some constants. So it'll be something like 1 is equal to all of this stuff, vy plus g upon k x upon h times q plus g upon kh, and then you got natural log of 1 minus kxq, right? So let's just call this whole thing as a, and this whole thing is b. So it just becomes 1 is equal to aq. I guess I'm making some sort of mistake. But what sort of mistake? should probably not be doing it like this. I should be dividing by g by k instead. So it just becomes something like hk by g is equal to, so vy k by g plus 1, and then you got x and q and plus this natural log stuff. Right, now we can call this thing as a and this thing is b, so just b equal to a q plus natural log of 1 minus kx q. Sure, that's better. So now we'll just define our f of q to be aq plus natural log of 1 minus kxq minus b. Yep. So yeah, what's f dash of q? This is going to be a plus, so 1 upon all that, right? Just minus kx upon 1 minus kxq. Yeah, that's the thing. So once again, the same as before. Just set this thing to be equal to 0. So you just have your q sub 0, that's equal to b upon a, and then again qn plus 1 is just equal to qn minus. That's it. Right, that pretty much solves it, I think. So once again, what's our b and all that? So your b thing is just hk by g, and your a is vy k by g plus 1 x. Yeah, that solves it, I think. I guess so. Fine. So I guess we found the solution. So it wasn't there in the previous question, was it? Right, it wasn't, but it will be in this question series. Sure. So question number 8 is just a copy of question number 7. Fine. Question 9. Question 9 is, he's given some equations. Find the length, so find the curve's unit tangent vector. Find the length of the indicated position of the curve. Indicated portion of the curve. Okay. And 0 to, oh, so the finding the length is very easy. It's just integration of dr, the magnitude, from t equal to 0 to pi by 2. So that is like integration of, so just, yeah, what's that gonna be? Oh, it's just a unit vector essentially. Oh, but that's not what we want. We want dr. So firstly, dr vector, that's going to be like negative 4 sine of t, dt, comma 4 cosine of t dt. Right. So the magnitude of that stuff, that's just 4 dt, it seems. Right. Just like 4 dt from t equal to 0 to pi by 2, which is like what? It's just pi by 2. I mean, it should be absolute value everywhere, like, you know, however one thing is, but yeah, it should be something like this, but who cares? I mean, yeah, okay, as long as your dt is positive. I guess that works. Okay, cool. So it's just pi by 2. That's, oh, so you want the tangent vector, so your r dash, right? So actually you want like the this upon the magnitude, right? So your dr hat, or I should say dr hat upon dt. I should say dr upon dt hat. Yep. That would just be something like negative sine t comma cosine t. And then the path, I'm just gonna call this thing as L. So L will just be pi by 2. And that's A. What about B? B is just going some curve, whatever. So once again, dr upon dt, that's gonna be, ooh, that's gonna take some time, isn't it? Okay, I think I know how to be doing this. I can think of it in terms of complex numbers. So just t plus iota t, right? Sure. So then the derivative of this would just be like 1 plus iota times e power t plus iota t, right? Yeah. Then the magnitude of that. Uh-huh. So the e power t doesn't really matter, it's just 1 plus iota times e power iota t. So something like 1 plus iota. And then, I mean, okay, so divide by the magnitude. That's what I was saying. So I should be saying something like the magnitude of dr, that would be just whatever is this thing's magnitude times this thing's magnitude, because e power it is just a unit vector. So it's just a square root of 2 e power t dt, right? And then dr upon dt hat, what's that gonna be? It's just cosine of t. Well, that's gonna be something like just 1, so cosine t, it's I sine of t. But then I guess that was the thing. Sure, that was the thing. Oh, there's also this thing. Oh, I didn't see that. So it's also 3tk. I didn't know it was a 3D thing. Right. 3tk. Yeah. That messes up things a lot. Oh, this is not very good. It's not even a unit vector now. Oof. Well, that's unit 1 vector. That's 4 over there. It's going to square root of 9 plus 1, 10. So this whole thing upon square root of 10. Yeah, not a very nice thing, but fine. We can still do it. We can still figure out the magnitude and all that. So the magnitude of dr by dt, what's that gonna be? Oh, by the way, it's something like 3 by 4, I guess. Oof, this is just not going good, is it? It's supposed to be 5 now, with minus 4 and 4. I see. I messed up somewhere. Okay, then the magnitude of this stuff. Okay, why you don't have to have the 5 over there? Hey, so it is 5, right? It's just 5 all the time, because of course it's 5. Yep, it's just 5 times of 5 by 2. Right, so that's your length. Ah, that was not bad actually. Okay, so you have kind of figured out what this thing is going to be, right? Yeah, it's cosine plus I sine of t, then you got plus iota of that, so just negative sine of t. So it's gonna call this c sub t minus s sub t, comma. Oh, by the way, all of this times e power t. I mean, I left that, but it should be. Right, and also the third component, which was e power t once again. So this was our dr vector upon dt apparently. So you can rewrite this as e power t and all of that. Right, that looks okay. I guess so. Isn't there a better way to be writing all of this? Nah, it's okay. Sure, so now what? Now that I've figured out what dr upon dt is, it's time to figure out the magnitude and the direction. And then the norm of all of this. So it's something like, okay, square, that's c square minus 2sc plus c square. Then you got s square minus plus 2sc plus c square, so let's cancel, it just becomes 2. So just 2 plus, I mean that is in fact 1, isn't it? It's just that. So 2 plus 1 square is just 1, so it's just something like e power t square root of 3. Sure. What about the direction? Let's divide by that. Right. So this is our unit tangent vector. And what's the path? So just gotta integrate e power t square root of 3 in that terms of dt from negative natural log of 4 to 0. So just 1 by 4, just like that. Yep, now we don't need all of this, let's move on. Question 10. Question 10 is, if a string wound around a fixed circle is unwound while held taut in the plane of a circle, its NP is the involute of the circle. In the accompanying figure, the circle in question is the circle x plus y square equal to 1, and the tracing point starts at 1, 0. Okay, cool, fine. The unwound portion of the string is tangential to the circle at Q, right, and leaves the radius measurement. Okay, derive the parametric equations. X equal to cosine to sine. Sure, okay, not a big deal. So it's been so the arc length that we kind of removed, that is just t times of 1, right? So this whole thing's length will just be t times of 1, and so this is just that, right? It's cosine t, sine t, that's q, and what about this one? So this angle is t, and you have a normal to that over there. So what angle does it make it? X-axis. Sure. So this will just be like t as well. This will be like 90 minus t. Wait, is this? No, it's not. Sorry. This will be 90 minus t. This would be 90 minus t. Right. So you just have sine t over there, and cosine t. So something like cosine t, right, comma sine t, plus, so this whole magnitude is like t, so plus t times of this, right? The angle that it actually makes is like t minus pi by 2, it says. Yeah, t minus pi by 2. Sure, because initially it was like equal to pi by 2, so whatever. So just, yeah, cosine of that. So that would be like sine, right? Yeah, but negative. Right, so just pi by 2 minus 2, so it's the same thing as that, which is pretty much just that. Sure, so x coordinate doesn't really change, so just sine of that. Just sine t, and this would be minus cosine t. Right. So it just becomes that x is equal to. So I mean, do you really like need a derivation for this? This kind of obvious. It's cosine t plus t sine t. And y is just. This thing is q. This thing is p. This thing is origin. Yeah. So y is just sine t minus t sine t whatever. Move on. Okay, next what we want to figure out is, oh, that's it, that's pretty much all you wanted to do. Fine. Okay, cool. Question number 11. So did they want me to like do this, in a more calculus way, or just, I don't know. I guess it's okay, right? Okay, so question, just the same thing as question 10. Find the unit tangent vector to the involutive circle at the point P x. Kind of expected. So we just got dr, that's equal to dx upon dt, dy upon dt on that, the magnitude of that divided by that. Sure, so this upon dt in fact. That's what? That's just equal to plus sine of t and then plus t cosine of t, right, comma. Right, that's the thing. So it's just equal to t times of cosine t comma sine t. That seems okay. Sure. So what you want is the unit tangent vector. So this thing hat, and that's gonna be equal to this thing, cosine of t comma sine of t. Which is weird, isn't it? Like, why would that be the thing? Cosine t plus sine t. That's the same thing as this vector. So it's like, oh yeah, it is in fact just, wow, that was unexpected. So I think this string is like normal to this at all points. Is that right? It doesn't look quite like that. I mean, this is very weird. No, it's not. Wait, but that is a tangent vector, isn't it? That's what the math is saying. That it is in fact that. I didn't do something weird. It's negative sine of t plus. Sure, that is the correct thing. Nope, it's all correct actually. So yeah, it happens to just be equal to that. The equations I got are also just correct, so it's okay, I guess. Fine. This is one of the properties, it seems. I'm just gonna actually just find it. I'm sure this could have been dealt with much easier using like complex numbers or something, but whatever. Question 12. Okay, find t, m, and k for the plane curves. Oh yeah, so the thing is, t is the tangent vector, the unit tangent vector. N is the curvature. If I no, no, okay, n is not a curvature. Heck, what was n? I don't remember. But okay, this kappa thing, this was the curvature, right? What was n? I think this was a normal vector. That's probably the only thing which makes sense. Yeah, it must be a normal vector. Just like perpendicular to tangent. Sure. It's just 2 dimensions, so it shouldn't be hard. What about like 3 dimensions? That would be a problem. I think I need to revise some notes. But anyway, in this case, it probably will be easy. Yeah, sure. So just r of t equal to this stuff, we can find the tangent vector. So t r vector upon dt, that gives you 2 comma negative 2t, right? So then your t, which is just the tangent vector, unit tangent vector, that's just, so 1 comma negative t, right? Just plus t square comma negative t upon square root of 1 plus t square. Sure. Now what? You have got this. You want to figure out the kappa thing. So the kappa thing is just yeah, so just have the curvature that's just equal to dt upon ds. Well, the magnitude of that, to be precise. And s is just like how fast it is changing or something. So you can rewrite this as dt upon t small t and then ds upon, so it's just like it becomes, so what's ds upon dt? It's just the speed at that point. So the magnitude of the velocity, or you could just say dr upon dt, essentially. Right. You just need to take a derivative of this thing. So just supposedly you just need the magnitude as well. So just the magnitude of dr upon dt. That would just be like 2 square root of 1 plus t square. Sure. I'm just gonna move everything outside. Okay. What else do you need? You just need this thing, so dt upon dt, which is like what? Oh, it's gonna be complicated. First, let's take the numerator, so it's like 1, this comes 0, 0 minus 1, square root of 1 plus t square, and then take this thing, so just plus 1 comma minus t, and then just like 1 upon 2 square root of 1 plus t square, that times of 2t, just cancels, it's just that, right? Yeah, I guess that's okay. Did I mess up something? Oh, I did mess up something. It's supposed to be 3 by 2, sorry for that. Just negative 1 by 2, right? Sure. And then this guy's going to be just 2t, cancels, right? So what does that leave us with? Is there something like 1 upon square root of 1 plus t square? You got 0 minus 1, and then it's a negative over there, so just negative t comma negative t square upon, this is extremely weird, 1 plus t square. This doesn't really look very good, but fine. Which is just something like 1 upon 1 plus t square power 3 by 2. Sure. Ooh. 1 minus t plus t square. Okay. That is going to be negative 1, isn't it? Yeah. So now you want to figure out the magnitude of this thing. Yep. That's even more problematic. Oh god. So the magnitude of this, and clearly you're also going to be dividing this stuff, so it just happens to be like completing one of these guys, so it just becomes, well, okay, just figure out the magnitude first. So something like dt upon dt, the magnitude of that is just square of that. Oh shit, I didn't sign up for this, did I? Wow, this is problematic. Yep. That too cancels, at least that's a relief. Yeah, there is no other way. Cool, just square it. So there's something like 1 plus t square plus t power 4. Shouldn't there be a better way by this? This thing square plus 1, that's what we're going for. No, there is no better way. Seems like this is the thing. It's just minus 2t minus 2t cubed, sure, plus 2t square and plus 1. This becomes 2 over there. I hope something gets cancelled. Okay, this becomes 3. T power 4 stays, so just something like 2 minus 2t plus 3t square minus 2t cubed plus t power 4. Right. Okay. And that upon this guy. Right, but they're not, because it's going to divide by that in any case. So your kappa just becomes this quantity upon all of that. Yeah. Wow. Not looking good. But fine, let's reach out, it seems. This is so weird. What do I do with this now? Well, the point was that sure. So the tangent vector is like that and it's moving, so that kind of gives us the okay, this was actually the going in, yeah, sure, that actually this is the acceleration vector, isn't it? So it's in the direction of dt upon dt that will actually find the normal vector. So you just want the unit of that, right? So it shouldn't be too hard. So it's easy to see that n would just be, so like given this, it's easy to see that the normal vector would just be something like 1 upon square root 2 and then 0. So not even that, but it's a 0 comma minus 1 directly. Yep, at all points in fact. And you also have this that actually gives you everything that you need for the center of curvature. So in case like anybody's confused what's going on, I'm just, so kappa is basically the curvature, n is the unit normal vector, which just happens to be dt upon dt, because obviously t is like, it's not exactly dt upon dt, but rather something like this thing, dt upon ds, right? So as you move along this, your velocity changes, right? So it's gonna assume like, oh, you're moving in a constant speed, then how does your speed change? Like if it was a circle, that would be happening. So yeah, you just ignore the effect of the velocity itself changing, right? So because that would be giving some sort of a tangential vector. So yeah, anyway, that's the point. What was I going to do? Right, that's pretty much it. Okay, 12th is done. 13th is show that this vector, okay, and this vector, they are both normal to the curve. Okay, I mean if n is normal, then this would also be normal. Sure. Hey, why is this? So it's negative n of this plus ftj is also plus ftj. Most likely a typo. This should be a negative or something. Yeah. Right. For the normal to this curve, r is equal to, so firstly, what's the tangent vector? So I'm just gonna call dr by dt first. So this dr by dt equal to f dash of t comma g dash of t. Sure. And you're seeing that this vector n, which is negative, I'm sure there's a typo in all of this. At the point ft gt, it should technically be g dash of t and then f dash of t, I think, right? This should be f dash, and similarly this should be plus and it should be minus, but no, somebody messed this up. Yeah, so look, I don't really have to calculate and show this because it's pretty obvious, right? Just take a dot product, you can see it's gonna be 0, so I'm just not gonna do that. Yeah, but okay, for the sake of completeness, let's just figure out the calculations first. So just, oh wait, it's actually multiple parts. Wait, what is this? A, B, C. They didn't give me any R vector. Oh, that's at the point. Fine, so I'm assuming that these should be A and B, and this is just some typo. So yeah, I'm just gonna do it as B and C directly, skipping A, whatever that was. So we just have R is so n should be minus g dash plus f dash. So this thing is f dash, this thing is g dash. So it's just minus 2 power 2t. 1, right? Minus n will just be negative of this thing, so just 2e power 2t minus 1. Cool. And you can see easily it's like the dot product is working and all that. Okay, what about C? Sorry for that. It's constrained somehow. Okay, that's because if you want this square root thing to be a real number. So dr by dt, it is like 1 over there, and just something like So then your thing is just like I'm just really getting really frustrated by all of this. I'm not even going to write what negative n is, but yeah, that does it. Question 13. Let's go to the next one. Question 14. Question 14 is find t and n. Just can you just stop? Really, like I'm just differentiating things one by one at this point. Just gonna write this as a 3 vectors or something like that. So just differentiate e power t cosine. Oh, I've seen this before, have I not? Oof. In this case, this is already 2, so this thing is like what? Right. Just e power t cosine t minus e power t sine t. Right, this thing is also just e power t, and then you got sine plus cosine. Cool. So that's our dr by dt. Whatever. Next, we just have the tangent vector itself. Just remove this e power t stuff. It's like not very good. And it's just gonna be 2, so 1 square root of 2 plus 4 e power negative 2t, because it doesn't have that, unfortunately. And then this is just that, so cosine minus sine, sine plus cosine, and then 2 e power negative t. Wait, did I mess up? Oh, I did mess up. This should be c. I thought it was 2t over there, so, but no, it's actually just that. So you don't have to do all of this. It's just this 1 by 2, then cosine command, cosine minus sine, sine plus cosine, and the k component is not there, so I'm just not writing that, but you should technically be writing that. Right, so you found n, sorry, you found t. You also need to figure out what n is. So n would just be like, take a derivative of this stuff. It's gonna give you something nice. So it's the same as before apparently, so just like what? It's not equal to that, but rather just negative of that. So it's 1.4, which is a negative of that. Yeah, it's okay. It's minus sine minus cosine, comma, minus sine plus cosine. That's what this n vector is. You also want the curvature, so kappa is just like this is making so frustrating really. Sure. It's just the derivative of this, the norm of that. Right. Which is like what? Well, we know that's going to be 2 into it's just 1 by 4. Something is messed up about all of this, isn't it? Oh, it's not. It's just going to be 1. Right, obviously. So this is just 1 over there. This will be just 1. No, this should be 1 upon 2, but fine. Yeah, makes sense. So the norm would just be 1 for dt upon dt, right? And that's why I'm just gonna keep it like that. Yeah, that makes sense. Okay, that upon the norm for dr upon dt, which just happens to be 2 e power t. Cool. So that's our kappa. It's right fancy. I don't know. That gives us everything, I guess. So it's just 1 by 2 e power negative t. Cool. Next question. Is find total curvature of the portion of a smooth curve that runs from s equal to s0 to s equal to s1 by integrating kappa from that's weird. The curve has some other parameter, say t, then the total curvature is this thing. What do you mean other parameter? So for example, you're given r of t, which is just a parameterized thing. Sure. Given a parabola, you can probably parameterize, that's not a big deal. Okay, so find the total curvature of the portion of a smooth curve that runs from, fine, by integrating kappa from the curve has some other parameter, say t. What other parameter? Fine, it's just this parameter. ds by dt, sure. Why is this thing there? Kappa v dt. Oh, because you want to be doing a ds. Yeah, makes sense. So just ds by dt times dt, sure. So yeah, so what you basically want is just this integral that you have capital K is equal to integration from t0 to t1 of the small kappa, the velocity, so just basically the magnitude of dr upon dt, and then you got dt over there. Cool. So the really just all you have to figure out is this and the dr by dt thing. Fine. Let's go. So a r is this stuff. So what's r dash? That's just -3 sine t, comma, sure, just 3 cosine t, and then you got what, 1. Okay, so it's the square root of 10, sure. I guess, yeah. So now what we want is the magnitude of this guy's derivative, so just right. Then you also want unit of dr upon dt, so basically just r dash, which was square root of 10, yeah. So just this thing upon that, so your kappa just happens to be 3 by square root of 10 upon square root of 10, which, guess what, is just 3. This is getting really old, isn't it? Whatever. So just 3 is the value. Wait, what? Oh, it's a number. That was unexpected. A helix has just, oh, this is unexpected. Right, okay, so it is in fact just a constant. Makes sense, it's like so symmetric in time in any case. So yeah, just 3. Then what? Right, so just want a total curvature portion of the helix from what to what? From t0 to t1, right? Okay, but like, what is t0 t1 here? What portion are you talking about? There could be so many different portions of the helix. It's just stupid. Oh, so okay, s0 s1 are probably like some values of this. I don't even know what is s. Really, I mean, you could be writing s in so many different ways that this just doesn't make sense. I guess what we will have to do is just figure out the total path or something. So just yeah, so this thing is just happens to be like, yeah, sure, so it's just square root of 10. It's like square root of 10 dt. Your s is just like square root of 10 times t apparently, right? So if it's something like that, then yeah, so what we want to do is just integrate 3 dt from, hey, why even integrate dt? You could just be doing s, right? So just ds from s0, because it's not a function like anymore, it's just a constant, so s1, it's just like 3 times of s1 minus s0, right? So a is just that. So the capital K thing is just 3 times of s1 minus s0. Cool, that makes sense. This is not dr, by the way, it's d tau. Yeah, I'm just gonna switch that. So to b is this thing, so just t comma t square essentially. Fine, from negative infinity to infinity. So ooh, that's gonna be very weird actually, but anyway, so that's your r. Then what, you want your t, which is just it's gonna get messed up real soon, I'm sure. But anyway, look this stuff up. It's not squared actually, so that's actually, oh, it is squared, sorry. Oof. Okay, so it's got 2t1, just cancels that out, just minus 4. Not plus. So it's to the power of 3 by 2. Right. So what we really want is just the curvature, right? So it's the magnitude of this thing. So something like square upon square root of short this thing, and that times the norm of the stuff inside. I don't really like the stuff inside. Let's just see what this thing is. So you got a 0 over there. Oh, that actually cancels some stuff out. Cool. And you got like 1 plus 4t squared, 2 times of that. So something like 2 plus 8t squared, and that one is 4 times. So it's just minus 4t minus 8t. Oh, that is amazing. So just 0 comma, not 0 exactly, it's minus 4t. So minus 4t comma this. I don't know what is for put a, yeah, I guess I get it. In that time, so what's gonna happen is just this is 0, that thing is 2 over there, so just well, we cancel that out. There's that. So we got minus 4t something is really messed up. Ooh, it's not supposed to happen. So it's 2 plus 8t square, right? And then just minus 8t square, nothing else. So just 2. So it's just something like minus 4t comma 2 in the numerator. Sure. So just norm of minus 4t 2 vector, right? So you can just take that 2 outside, just like 2 upon 1 plus 4t square to the power of 3 by 2, and then you just got like 2t and 1. So that's just like once again just 4t square plus 1 to the power of 1 by 2. So it basically just like cancels that. So just 2 upon 1 plus 4t square. Right. So this is just 2 upon 1 plus 4t square. So you want to integrate this from negative infinity to infinity, which means, yeah, it's just negative infinity to infinity. Oh, by the way, what's dr by dt? The magnitude of that. We need that, right? Sure. So it will be that times of okay. So just once again, just square root of 1 plus 4t square just pops out of somewhere. Just 1 of 1 square root of 1 plus 4t square, and then this thing. That's the thing. So you can think of it as integration of just dt upon square root of 1 plus t square. Right, now guess what we do over here, t equal to tan theta. So this just turns out to be integration of secant square theta d theta upon this 1 plus secant square theta. So 1 plus tan square theta, secant theta is just that. And this is from theta equal to, it's going to negative infinity. When does that happen? And infinity, that's minus pi by 2 to pi by 2, right? So it's just one of, so just secant theta, that's like 1 upon cosine theta, sure. So you can just write it as secant theta directly. Yeah, that makes sense, I guess. I mean, okay, cool. So just 1 upon cosine theta. So what do we do now? Just the integration where it's like very well known. It's just natural log of secant theta plus tan theta. And it's from negative pi by 2 to pi by 2. So at negative pi by 2, you just have like, what? Just negative infinity. That is really messed up. I mean, it's already divergent thing, isn't it? Negative pi by 2, it's going to some problematic things. Cosine theta, it's becoming 0, not a good look. We'll have to do some limiting case and all that. So just negative x to x, something like that, right? So just, what the hell, why did it turn out to be like this? Square root of 1 plus 2 square. Why do I feel like this is actually a divergent thing or something like that? What about natural log? Oh, that would be also divergent. And this is actually, no, but it's like that. Oof. You can use symmetry. Over here and just say, oh, you're just gonna have to. That works, sure. And then you can think that, okay, this is slightly less than, just shit. What is this? So it's something like it's less than equal to infinity of dt upon t. That's a problem, because you can't just do that. No, you can't. That's not a valid way to be dealing with it. And so you just have to deal with this like that. So just cosine theta now. This is 1 plus sine theta at pi by 2. 1 plus sine theta at minus pi by 2. Ooh. I have a negative 1 over there. It's actually going to infinity. Well, if it's not going good. But it is certainly, oh, the absolute value, right? But that doesn't matter actually. What am I doing? The cosine, that should cancel out. Okay. Yeah, what if I just used 0 over there, like instead of that? So it would just be like 1 essentially. That would be 1. So it's 2. It would be like natural log of 2. Right. So it's something like 2 natural log of 2. I think this quantity is just 2 natural log of 2. Yeah. That was bizarre and I don't know why that happened. Why did that happen? So complicated. Never mind, just move on. Anyway, sure, just move on. Let's see what we get. 15th is done. Question number 16. Find an equation for the circle of curvature of radius. So okay, so find the equation for the circle of the curvature of this curve. Circle of curvature. Okay, fine. R of t, fine. At some point, cool. Just figure out what r dash is and all that. So r is t comma sine t. R dash will just be 1 comma cosine t. The tangent vector is just like, so just 1 comma cosine t upon square root of 1 plus cosine square. She's really something, but whatever. Okay, cool. Then what? You want a normal vector obviously, just so dt upon dt, that's gonna be like what? That's something like 0 comma negative sine upon square root of 1 plus cosine square. square, and then let's have this other stuff, just minus 1 upon 2. So then that 2 is gonna get cancelled in any case. So yeah, just got cosine, but then we got also negative sign, so just sine cosine of 1 square upon plus cosine square, and 1 comma cosine. Make sense? Sure. Let's try to combine. Oh, it's supposed to be 3 by 2. So something like upon plus cosine square of 3 by 2. Let's see if we can combine some stuff. So you got 0, okay, plus sc, sure, minus s times of 1 plus c square, just minus plus, right, minus sc square, and then you got plus sc square, so this just cancels, so minus s plus sc. Right, that makes sense. That's our thing. So your n thing is just, you discard all that. The s thing is also discarded. You know, you can just factor out some stuff actually. Sine upon 1 plus cosine square of 3 by 2. And it's got like what, cosine comma negative 1 plus cosine. Sure. So then, right, so your normal vector, that will just be like, normalize that, so c square plus 1 plus c square minus 2c, something like 1 plus 2c square minus 2c, whatever, is that 1 upon I really hope I'm doing something correct. I don't know. Right, move on. So that's a normal. You also need a kappa thing, the curvature. So it's just you already have that magnitude. Sure. So just like s upon 1 plus c squared power of 3 by 2. That times this thing's magnitude, which is we figured out is this quantity. Okay, all of that upon the magnitude of dr by dt, which is square root of 1 plus c square. Sure, so just happens to be, we'll just square that now. Right, now you got this. Like what was I going to find out? Right, so you want the point to the center of curvature, right? Our rho thing, that's just like 1 upon this stuff. It's just 1 plus cosine square squared upon sine square root of 1 minus 2 cosine plus 2 cosine square, right? Then the center is just whatever point you are on. The point is t comma sine, right, plus the normal vector times this rho thing. So just plus 1 plus cosine square squared upon sine, and then this stuff 1 minus 2 cosine plus 2 cosine square, whatever that quantity is. Yep, that's your center. Cool. So then the whole thing just boils down to like, oh, this is really problematic. Can I actually simplify this further? I don't feel like I can. Nope, this is the most simplified thing yet, I think. Isn't that right? Let's just actually try to see what the numerator is. So just 1 plus 2 cosine plus cosine square, that times of first the cosine, so just cosine plus 2 cosine cubed plus, sorry, cosine square plus cosine cubed, and minus 1 of this, just minus 1 minus, no, you shouldn't be doing that, you really shouldn't be doing that. Okay, that didn't go so well. I mean, okay, it's fine, that's just how it is. So you got c and you got rho, so it's something like x minus, so x comma y or p, whatever, so just p minus c squared. This thing should be equal to rho squared. That's your circle. So you just have to calculate all the quantities now. time to calculate some stuff. So your r will be at, so we want at t equal to, so it's pi by 2 comma 1, so it's t equal to pi by 2. Sure. So this will just be like 1 comma 0, and this will be just 1 comma 0 as well. You know what, this quantity, so it's just pi by 2 is 1, that thing is 1, it's just gonna kill itself. So just 0 comma negative 1. Oh, that is like really simple apparently. So cosine is 0 everywhere, so you don't really have to worry about that. Just 0 comma negative 1. Kappa is just, you know, there's just 1, and we got 1 0, sure, just 1 basically. And a row would also be 1 obviously. What about this point? So it's n times of a row, right? I mean, you can do this thing. So your center will just be something like pi by 2 comma 1 plus, so this is 0, this is like, if it's not s, it's a cosine over there, right? So it's just 1, this thing is 0 minus 1, whatever, just 0 minus 1, that's 1, this thing is 1, sure. So that's just like pi by 2 comma 0. So all you really have is like x minus pi by 2 square plus y squared equal to 1. That's your like equation. Okay, that's 16. Move on. Question number 17. 17 is, wait, what? The curve parameterizes the graph of, okay, fine, whatever. Find the parameterization of the oscillating, what is that, circle for the parabola when x equal to 1. Even just the circle of curvature, sure. For the parabola, right? I think we already did that, right? So we found some stuff for the parabola. Yeah, it was this stuff. Right, cool. So also want the n thing. Hey, so you can just directly figure out that. Cool. That's actually gonna be awesome. Right. So you want at x equal to 1. So at t equal to 1 basically. Just like 1 comma 1. This thing is 1 comma 2. This thing is, I want this 4t square, so t equal to 1, just 5, so like square root of 5 basically. Just 1 upon square root of 5 comma 2 upon square root of 5. What about this quantity, which is 0 comma 2 upon square root of 5 minus, so 4 times of 1 comma 2, so just 4 comma 8 upon 5 square root of 5, sure, which happens to be what? Why is this so long time? Wait, so I kind of simplified this, didn't I? Yeah, I did somewhere. Never mind, you can just calculate it directly. So this is like what? 1 upon 5 square root of 5, you are 0 comma 10 minus 4 comma 8. This is something like what? Just minus 4 comma 2 upon 5 square root of 5. Yep, that is your thing. So just got n is minus 2 comma 1. So got, sure, so it's just like minus 2 1 upon square root of 5. That is your n, and that pretty much gives you everything, right? So what is your magnitude of dt by dt? And that would just be 2 square root of 5 on all that, just 2 by 5. So 2 by 5, then upon the r dash thing, so just once again just square root of 5 away. Yeah, that's the thing. Okay, cool. Then your row will just be like 5 square root of 5 upon 2. So then n row, or row n I should say, that's just cancels with that. Sure. Just 5 by 2 comma negative 2 comma 1. Right. Your point is this thing. So that's your circle. Which is okay. Just gotta do this thing. Just minus 10. Never mind. So just minus 5 comma 2.5. So this would be something like x plus 5 squared plus y minus 2.5 squared. That's equal to your rho squared. And what's a rho? A rho is this. So that square is like 25 times 5 is 125 upon 2, which is like 62.5. So yeah, that's your thing. Cool. So that gives so that completes this assignment. I mean, I say it's completing it, but really just you have to code all of this. So let's just get started with that now. Right. I'm gonna use. I guess that's okay. Yeah, some random stuff. Right. So I should make a new folder. Who knows? Yeah, I guess it's just better to make a new folder. So this will be multi-variable calculus. And this that I must have tutorial 2 dot come on, what's wrong with you? No. So I'm gonna need some stuff. Yeah. Yeah, I'm gonna need this a lot actually. I also need NumPy, most likely. Sure. First, let's run this. Okay, now let's just get started. So this is just libraries. This will be just tutorial 2. Yeah, I guess I'll just run that again. Sure. Okay, so what I want to do is questions. Okay, time to code some stuff. Actually, before coding, I guess what we should be doing is, so why won't it let me minimize this? I guess because of that. Sure, so will it let me? Oh yeah, it will let me do that. Okay, it won't let me do that. Fine. So question 1 is just this. So what I'll do is just like I'll copy this and then I'll just paste it there. I hope that Jupyter Notebook works that way, because I actually don't know, but you gotta try. Because who knows, it might actually be working out. Basically, I'm just making like a report in a way, like yeah. Okay, so it's in the clipboard. I don't know if I can just paste it. Just mark down and paste that. Sure. Yes. Oh, it does work. Okay, cool. Fine. Actually, if I can do that, then why not just paste it directly over here? Right, that works. Okay, so question 1, it was just this thing. You wanna plot what? R of t equal to 5. So I'm gonna plot this till 4 pi. So t will just be equal to what, a range, I guess. A range from 0 to 4 pi. 4 is of pi. Let's say 1000 or something like that. Cool. Sure. So x will just be like t minus sine t. y will just be minus cosine of t, and I just want to plot x comma y. That's gonna work. That didn't work actually. Yeah, something didn't work out. Suppose we could, oh, I guess just make this like 4 pi or something. Hey, why did it not work? Like, this should, right? Oh, so A range doesn't work like that. Yeah, right. Let's just use line space instead. For A range, you actually have to give a resolution first. Sorry for that. Happens sometimes. No, I do not want to do anything with you. Right, so that's how it is. So this will be like 0, this will be 2 pi, 4 pi, whatever. So I'm also going to plot some points. So I'm going to plot 0 comma 0, sure. So 0, so we just circle, right. And I actually want to label this, so I don't know how to do that. I guess I can just put a label, bar label. I don't know what that does. Yeah, I have no idea what that does. How do you annotate this thing? Just point polyint. No, I don't want that. Text. Yeah, I guess. Oh, it's xy, the string. Sure. And I can also make the point itself, right? Not the point, the plot. Plot 0, comma. Let's see what that does. Yeah, sure. That is exactly what I wanted to do. So it's not OHL, right? Instead I'll just write just 0. Okay, cool. Then what? 2 times of pi? Sure, 2 times of pi. This will be like that. It's just 2 pi. I'm gonna put some nice latex stuff. Cool. And then now it will be 4. Let's run that. Right, so that does it. You also can probably plot the whole line itself, so just plot the x-axis. Just plot what? So it's going from 0 to 4 pi, right? So it will just be like the first point is never mind, just 0 comma 4 pi. And it's all 0 0. Oh wait, why didn't you just do? Oh, because I just put that. Cool, that's gonna work out. Yeah, that is the thing, which is kind of matching. It's what we thought it will. Sure, okay, that's a plot. That's question 1. I see. So this won't work like that. I will have to put the image at some other location. Oh, so you don't actually just. I see. So I just actually have to paste it like that. That doesn't work. So now what do I do? I mean, it's not in the screenshot, is it? Okay. Oh, okay, that's how it works. Cool. This is very weird, but whatever. Okay, so that's your question 1. Let's go to the next one. Okay. Now, once again, the same as before, I'm just gonna copy that. So you want to evaluate these integrals. I mean, that's kind of easy, isn't it? Yeah, so the answer will just be that, this stuff. So just the A thing, that is natural log 4 comma natural log 4 comma natural log 2. B will just be so I should actually be putting the hat key stuff. Sure. Because that's like the correct notation apparently. Yeah. Okay. Yeah, that's gonna work out. Oof, that didn't work out. Okay. I shouldn't be surprised actually. That's fine. Yeah. So I think I need some space over here. I hope that actually gives me. Yeah, I mean, it's okay. I guess I can just put something like this. Yeah, that's better. Fine, so question 2 is done. Let's go to the next one. What do you mean 3 cells again? Okay, actually, you know what? This is probably going to take some time. So, how about I see you in the next video? Fine. So, I'll see you guys in the next video. I just have to like code some stuff so that like I can find the numerical solutions to some things. But that's it. So, I'll see you guys in the next video. Bye.